Let's prove this fundamental connection between the spark and the mutual coherence, as it is key in making uniqueness claims for the general case. The proof will be based on the Gershgorin disk theorem, so let's start by presenting it. We are given a general square matrix A of size n by n, and we are wondering about the values of its eigenvalues. In our discussion, we shall assume that the entries of A could be complex numbers. Gershgorin theorem defines n disks of this form, each referring to a different row in A. This disk looks at the kth row, uses the main diagonal element AKK as the center of the disk, and defines the radius to be the sum of the absolute values of the rest of the element in this row. Geometrically, it looks like this. AKK is the center of a disk defined over the complex plane. Gershgorin disk theorem states that all the eigenvalues of A must reside in the union of the areas of the n disks we have just defined. So, draw all the disks, and this defines where the eigenvalues of this matrix can be found in the complex plane. An immediate and important consequence of this theorem is the following property. Consider a matrix A that is real and symmetric, having positive entries in its main diagonal. Such a matrix is called diagonally dominant if for each of its disks the radius is strictly smaller than the value of the center point. As such, the disks of this matrix never overlap with the origin, and thus A is invertible. Moreover, since A is real and symmetric, the n disks are positioned on the real axis and their eigenvalues are known to be real as well. Thus, the minimal eigenvalue of A is bigger than the leftmost point in these n disks. Being strictly above 0, thus A is positive definite. And now we come to prove the spark coherence relationship. Let's extract S columns from the matrix A and build the submatrix AS. We compute the Gram matrix referring to AS, given as AS transpose AS. We denote this as GS, and clearly this is a leading minor from the general Gram matrix of A. As such, we know that its main diagonal contains 1s, and the off-diagonals are all in the range minus mu to mu. If we can claim that GS is positive definite, this means that AS has S linearly independent columns. If we could make this statement with respect to any subset of S columns, this means that the spark of this matrix is strictly above S. This is the strategy we shall follow. We shall propose a simple condition for GS to be positive definite. Let's require that it is diagonally dominant. The disks of this matrix are all centered around the point 1 on the real axis, since all the main diagonal elements are the same, being 1s. The maximal possible radius for these disks is S minus 1 times mu, and thus if we require 1 to be bigger than this radius, we get the diagonally dominance property. Rearranging terms, we see that S should be smaller than 1 plus 1 over mu, in order to guarantee that GS is diagonally dominant. This implies that GS is positive definite, and thus any S columns of A are linearly independent. We conclude that the spark of the matrix could at best be 1 plus 1 over mu, as claimed. We summarize this discussion by comparing again the uncertainty rules we got for the 2-ortho and the general case, both posed using the mutual coherence. In the 2-ortho case, the uncertainty bound is 2 over mu, while in the general case it is 1 plus 1 over mu. While the two look similar, clearly the general case is weaker, and this is expected. The special structure of the 2-ortho leads to many zeros in the Gram matrix, and those enable to get a nearly twice stronger result.